one might wonder about the power dissipation in an RLC circuit. From what we know before, the generator, the power source, is going to provide power. Resistors dissipate power. They generate heat. However, capacitors and inductors store and release energy. A capacitor is going to store the energy in the form of charge and it's going to release it. The inductor is going to store energy in terms of magnetization and releasing it. So power loss is going to be only in the resistor in an RLC circuit. And since in an AC circuit, our current is going to follow a sine wave function, and since the voltage across the resistor is going to change depending on the time in the circuit, power is going to change in time from large to small values. And as we discussed in a previous chapter, then we talk about the average power dissipated. And the average power dissipated, we said it's 1/2 I max, the maximum current, times the maximum voltage across the resistor. 1/2 of that. Now, we also said this is equal to IRMS VR RMS, or R I RMS squared, or VRMS squared over R. All of these apply. Now, remembering that in the phase diagram, we can look back here. This is the voltage across the generator. This is the component due to the inductor and the capacitor. The only component that's lossy is the component parallel to the resistor, which is the X component in this particular diagram. So we can express the power loss in terms of the voltage across the generator. So it's going to be the same thing, except realizing that VR max is actually Vgen max times cosine of phi. So the power dissipated in terms of the voltage across the generator can also be written, this 1/2 can be embedded in these values to get the RMS values, IRMS, Vgen RMS, cosine of phi. So you take your pick. It's IRMS V RMS or IRMS Vgen RMS cosine of phi. Now, in summary, in an RLC circuit where we have an AC generator connected to a resistor, capacitor, and an inductor in series, the voltage across the resistor is given by Ohm's law, IR, with the voltage in phase with the current. The maximum voltage across the capacitor is given by I max XC, where XC is 1 over 2 pi FC, and that voltage is going to lag I by 90 degrees. The voltage across the inductor is VL max. It is equal to I max times XL, the inductive reactance, with XL given by 2 pi FL. And it leads the current by 90 degrees. The voltage across the generator is going to be I max times Z, where Z is the overall impedance. We can find it by square root of R squared plus XL minus XC squared. its phase angle is the inverse tangent of XL minus XC over R. It can lead or lag I depending on the values of XL and XC. Power is dissipated only in the resistor. The average power is given by IRMS, VRMS, cosine phi. When drawing the phasor diagram, we draw the resistor vector to the right, the length given by VR. Remember, as an alternative, we can draw just R if we're looking for impedances. The capacitor vector, we draw it downward with the length given by VC, or if we prefer to do impedances, the length given by XC, and we draw XC. The inductor vector, we draw it upwards, the length given by VL, or if we'd like to do impedances, it's XL. The generator vector, we add the first three vectors, either representing the impedances or representing the vectors, and the length is given by Vgen. Now, for example, in here, so this minus this is going to give us something like this. That's VR, so that's my Vgen. In this case, it is lagging, not leading the current. And we can see it here at a different time, and we can do the same kind of analysis. The whole phasor diagram is going to rotate in the counterclockwise direction with the vertical components given the instantaneous values of the voltage across each of the elements, this being, for example, VL, VR, VC, and Vgen. In this case, Vgen is 0 since it's parallel to the horizontal.